Hi, my name is Madison Smith, and this is my Lab 5 on Faraday's Law. So the purpose of this lab was to compare our calculated results with a computational model of a bar magnet dropping through a tinfoil tube and to demonstrate Faraday's Law. So Faraday's Law is when there is a change in the magnetic field on a closed loop. So in our case, we had a bar magnet falling through a tube. It's the source of a curling electric field that happens around the loop, and this will cause an induced current on the loop in the direction of the curling E field, which will produce a voltage EMF equal to the change in flux. And so Lenz's law is that there will be a magnetic field from the induced current created in the opposite direction of the change in flux to offset that. So this is a free body diagram to kind of explain that. So on each one of these loops, we're going to have the curling E field and then the current, which is in that direction. And then we're going to have an upward force on the magnet that is created from the induced current to offset the magnetic force that is going downward. So the procedure is that we dropped a bar magnet through a roll of tinfoil 5 times, just the average time it took for it to travel. So the average time was 1.632 seconds. It took longer to fall through the tube than it would in free fall because of that upward force that I just talked about, and then we're going to compare this value with our computational model. So for our computational model, we set our initial conditions with what we used for the experiment. We calculated the magnetic field of the bar magnet, which is what I used for lab 3. I just copied it over. And then we calculated the d phi over dt, or the change in flux. So we used a formula for that. And then calculated the magnetic force due to each ring, as well as the current, and then summed all those together to get the total magnetic force. And then using the magnetic force and the gravitational force, we calculated F net, and then used that value to plot the velocity and the position of the bar magnet going through the tube. So this is the output that we received. So this is the magnet going through the tube. And then this is what our output is for the velocity versus time graph. As you can see, the time in the tube was 1.32 seconds. So I'm going to talk about that a little bit in a second, but this is the graph that we got from the output. So interpreting our model, so it basically is asking which color corresponds to clockwise viewed from above or counterclockwise, and how do you know when the magnet is going through the tube. So I said that red would be counterclockwise because the curling E field induced from the magnetic field in the wire, and because the curling E field set by our right-hand rule says that it is counterclockwise because it's going to offset the change in flux. And so what happens to the dynamics of the system when you flip the magnet around? So the current's going to flow in the opposite direction, clockwise, so that means that the color is going to be blue. So that kind of explains which one is red and which one is blue for counter and clockwise. So part 2, so how does the total time in tube of your real world experiment compare to your computational model? So for our computational model, we got 1.235 seconds, and for the real world, we got 1.632. And so this can have be for a lot of reasons, but mostly it's due to human error. We're not dropping it 100% perfect into the tube every single time. It could have been at a little bit of an angle or dropped from a different height. And also I used my phone to calculate the time in the tube, so it could have been an error on my part with reading the times. And so what does the shape of the velocity versus time plot tell you about the forces? So the magnet actually reaches its terminal velocity, which means that the magnetic force is going to be equal to the force of gravity, and that there's no acceleration happening while it's in the tube. So the forces are going to equal. So what if the resistivity of the conductor were reduced to as close as possible to 0? So if R would get really small, then I will increase, and so the induced current would get bigger, and so the magnetic force from the ring pushing upward would cause the magnet to slow down even more. And so if you cut holes or slots into the tube, what would happen? And so the current wouldn't be able to run through the rings. The magnetic field would be smaller. It wouldn't push upward as much, and so the magnet would end up falling faster. So this is all I have, and please let me know if you have questions. Thanks so much.